So what is the current voltage drop and power of each of three appliances connected in parallel to a 72-volt source? To a 72-volt source. The resistances of the three appliances are 12 ohm, 24, and 8. So we are looking for what is the current voltage drop and the power by each of the three appliances. And I'm giving you 6 minutes to try. Let's see what you can produce within the 6 minutes. Let's see what you can do within 6 minutes. And I'll take over right after the 6 minutes. Beryl, you are welcome.
Thank you, Mr.
Eliana, we are looking for what the question says that what is the current voltage drop and the power by each of the three appliances connected in parallel. Connected in. Okay, so we are looking for current, voltage drop, and power in each of the three appliances respectively. Start with 6 minutes. So it's 7:10. So 7:16, whether you manage to finish or not, you are stopping. So we could do a new thing. It is. It is. I'm seeing Yabua. Who is Yabua? Yabua. Yabua Buami. Yabua Buami. Who is Yabua?
Why?
Who?
Mr. Why? Why?
Why?
Mr. Why?
Israel, what is it? Israel, you the one. Please, if you've just joined us, don't worry. We'll discuss it, okay? Or after the lesson, I can send you videos. This is under current electricity. Current electricity. Ishra, are you Yabua?
Please, I'm not a boy, but
The
the bus.
The bus. Okay.
It's too many.
Okay, Mate. So you have 5 minutes to end. Don't worry if you don't understand, we are going to go through it. So relax and then watch. I think the first area we can tackle, and we can solve this without any calculation. That is the aspect of the voltage drop. So the voltage drop across all the appliances must be equal to 72 volts. So there will be a voltage drop of 72 across the 12 ohm resistor, 12 volts across 24 ohm, 72 volts across 8 ohm resistor. This is because of the fact that all three appliances are connected in parallel. When loads or resistors are connected in parallel, they have the same voltage drop across all of them. The second thing is, let's look at current. Let's look at current. From Ohm's law, voltage is equal to IR. If voltage is equal to IR, then current would be equal to V on R. So if I'm to calculate for the voltage drop across R1, okay, let's assume this will be the main current I. What is coming into R1 will be I1. What will come into R2, we are calling it I2. What will be coming into R3, we are calling it I3. So if I want I1, current is voltage over resistance. So the voltage drop across this, which is 72 over the resistance of R1, 12. And what is 72 divided by 12? What is 72 divided by 12?
Ampere.
Pardon?
6 ampere. 6 ampere.
So this is 6.0 ampere. I2 would also be V over R2, which will also be 72 over 24. And what is 72 over 24?
3.0 ampere.
So 3.0 ampere. I3 would also be V over R3. And this is 72 over 8. What is 72 divided by 8?
9.
Pardon?
9 ampere.
So this is 9.0 ampere. Therefore, the total current coming from the source I will be equal to I1 plus I2 plus I3. Therefore, total current will be 6 plus 3 plus 9. And this will total, what will be the total current?
18 ampere.
So 18.0 ampere. So this, we've calculated for the total current flowing through the circuit. Eliana, your hand is up. What is your secret?
Mr. Area, please,
Hello.
why did you just solve the resistance and parallel?
We will do that. We can do that. We'll come there. Okay. Okay, the question we are looking for current, voltage, and power. Determining the voltage drop is so simple. Then we came to current. We are done with current. The next move is to look at power. Arabia.
Mr. Dua, please. I thought you said we should find the current for each. So why did you find the total?
I'll use it later. That's why.
Okay.
But the question is about individual currents into the resistor. But because I'll use it to confirm something, the reason for which I totaled it. All right. Now,
Yes, please.
power, electrical power is equal to current times voltage. We can also derive another formula. If current is, power is current times voltage. Okay. Current times voltage. Then, using Ohm's law, V is equal to IR. We can substitute this V into the power formula to give us another formula for power. When I do the substitution, I have I times IR. And so I have power to be equal to I squared times R. Another relation for power. Another relation is that from Ohm's law formula, when I make I the subject, I have V on R. If I substitute I into the power formula, V is equal to, in place of I, I'm going to put V on R. So I have V on R times V. I have V squared over R. So these are the different formula or relations for electrical power. Electrical power is the energy used per what? The energy used per time, or work done over time. Let me ask you, if I have 10 watts, the SI unit of power is watts. Okay. If I have 10 watts bulb, 20 watts bulb, and 25 watts bulb. If I ask you to make a choice, pick one, which of these three will you take and why? If I ask you to make a choice, which of these three bulbs will you choose and why? Andre, among the three, which of them will you pick and why?
Yeah.
Yes, Mr. Andre. Okay, Andre is engaging the brain. So let me make it open. If you are ready with your choice, let me hear from you. If I ask you to make a choice among the three, which one would you use or will you pick? And why? I think the why is scaring people from making a choice.
Sir,
Gerald.
please, I'll choose the 20 watts because
Why?
so if you choose the 10, your bulb will not be bright. If you choose the 25, your bulb will be bright, alright, but for the current situation, Ubeboka, you'll be paying a lot of prepaid. So
you pay so much.
yes, sir.
Okay,
So I'll rather
I get you. Adibia, your hand is up. Maybe you want to make a choice.
Mr. Dia, please, all the current options you've given are very small as
The
compared to
power.
what we use.
I mean, the power.
Yes, the power.
Uh-huh.
Apparently, a bulb uses more than 25 watts, so that's very, very small. We use more than that, so I'll choose the 25 because 20 and 10 will be too dim for my liking.
Adibia, do you know that the LED bulbs we use in our homes? Okay, some have wattage as low as 18 watts. The LED bulbs.
Hey,
Is that
really,
okay?
Mr. Dia, I didn't know that. Okay, but maybe currently, but the last time I checked, it was 90, around 90 thereabout.
Oh, what I have here is 50 watts. Okay, all right, let me go on. You see, those days we were using incandescent bulbs, and Energy Commission introduced energy-saving bulbs. And we switched from the incandescent bulbs to energy-saving bulbs. Now, if I'm to make a choice, okay, fine, depending on what you want, as Gerald said, depending on what you want, you can make a choice. But at the end of it, when you choose bulb with so much power, wattage, whose power is high, be ready to pay more. Because when we talk of power is energy over time. So the SI unit is joule per second. But this was honored to my good friend Watt. And so joule per second was changed to watts. If I pick bulb whose wattage, power rating is 10 watts, technically what it means is that this bulb would convert 10 joules of electrical energy to light energy. Okay, the function of the bulb is to convert electrical energy to watt energy. So if I pick a bulb whose power rating is 10 watts, it means this bulb would convert 10 joules of electrical energy to light energy every second. If I pick 20, it means this bulb will convert 20 joules of electrical energy to light energy every second. In a second. 25. So it means your electrical heaters in your homes, whose rating 1,000 watts, means that 1,000 joules of electrical energy is converted to heat energy every second. So when you pick bulb whose power rating is high, then there will be greater consumption of electrical energy. So be ready to pay more. So basically, that is what it means. Is that okay? So let's go back to calculate for the power. So I've given you the different relations or formula for power. Okay, you can use any. You can use any of them, but for the sake of time, let's settle on IV. Let's settle on IV. So using P is equal to IV, find the power. P1. P1, of course, would be equal to 12 times 72. I can also calculate for P1 using 12 squared times its resistance, which is 12. What did, okay, no, we had, the current is 6. Sorry, the current is not 12, it's 6. So 6 times 72. This is also the same as 6 squared times resistance 12. And both must give me the same result. So confirm. What is P1?
432 watts.
So when you multiply, when you pick it for both, are they giving you the same results?
Yes, please.
432 watts. Okay, P2. P2, of course, would be 3 times 72, which is also equal to 3 squared times 24. Yes, what's it?
216. 216 watts.
216.
Yes, please.
P3. P3, we have 9 times 72, which is also equal to
648 watts.
I'm coming 9 squared times 8. Is that is equal to what?
648 watts.
Now, if in case I'm asked to calculate for the total power, it means P total must be equal to P1 plus P2 plus P3. And this would be equal to P1 432, P2 216, P3 648. Please total everything for me. Inshira ya mesresre. Inshira.
Sorry.
What is the total power?
1,296.
Hey, Togo, give it to me in numbers.
12961.
1296
1.
1296 watts. Another way to also do this, you see, power is equal to IV. So if I manage to get the total current, okay, if I manage to get the total current and then the voltage, it must give me the same thing. So let's multiply 18 by 72. Multiply 18 by 72. Hello. So it is also giving me the same results. 1296. Another way out is that power is also equal to I squared times R, meaning a square of the total current times the resistance. So your work now is to help me get the total resistance for this arrangement. What is the total resistance for this circuit? So calculate that for me. Barry, are you there?
Yes, please. Please, it was 4.
It was what?
4.
4. Hey, Barry, I don't understand what you are saying.
Please, the total resistance across the entire thing. When I did it, I got 4.
You got 4. Let's have somebody to also a seconder. Okay. Yes, which is true with the total resistance.
The total resistance is 4. 4
It's 4. Okay.
4.
So
Yes, 4.
so let's 18 squared times 4. Let's confirm 18 squared times 4. Oh, Grace, you.
1296.
Pardon? 1296. All right. So the same results. Okay. I'm giving you one to work it out yourself. I will not come in. So an exercise to be done in about 5 minutes time. So we have So the ammeter reads 3.0 ampere. The ammeter reads 3.0 ampere. R1 is equal to 20 ohm. R2 we don't know. R3 is equal to 30 ohm. So we have R3 equal to 30 ohm. The source voltage is 24 volts. The source voltage is 24 volts. Now listen to the question. Are you ready? Do I read the question?
Yes.
All right. So what is the equivalent resistance in the circuit? What is the equivalent resistance in the circuit? Equivalent resistance refers to total resistance. Don't forget. Then 2. The current in R1 is, or what is the current in R1? So we are looking for one equivalent resistance then 2 current in R1. Three, what is the potential difference across R3? What is the potential difference or voltage drop across R3? Then 4. If the ratio of the current in R3 to the current in R2 is 4:5, what is the resistance in R2? If the ratio of the current in R3, so I3 is to I2 is equal to 4:5. What is the resistance in R or of R2? Then the fifth question is that the power supplied noted. The power supplied to the circuit is, you have to calculate for the power supplied to the circuit. All right, so quickly go through it and then let's see.
Mr. Ja, please, what's the
what's at the top there? I can't see anything.
We are giving the source voltage to be 24 volts. Then
Okay.
this is an ammeter. The ammeter reads 3.0 ampere.
Okay.
Okay. We have
And
R1. R1 is 20 ohm.
Okay.
R2, we don't know. R3, that is 30 volts.
Thank you.
Welcome. So let's go through it quickly and then continue.
Sir,
Yeah.
sir.
Uh-huh. Gerald, I'm listening.
Sir, please. The voltage, I can't really see it well. Is it 24 or 240?
It's 24.
Voltage is 24.
Mr. Dear,
Hello.
please, I can't see the screen.
What's the problem? Blurry.
Mr. Dear, it's fine. I've seen.
Okay. 2 minutes. Two minutes more. Inshira,
Instead, yeah.
Andre. Okay, so what is the equivalent resistance? What is the total resistance? Yes.
8
Pardon?
8 ohms.
8. How did you get that? Can you share with us?
I use V is equal to I times R, and from the relation R will be equal to V on I, and from the diagram, the V is equal to 24, and the current I is equal to 3. So R is equal to 24 over 3, which is equal to 8.
Please, are you getting where she's coming from?
Yes.
So we are looking for the total resistance. Okay, and we have EMF of the source, which is 24. We have the total current in the circuit. So our Q or equivalent will be equal to the total voltage, which is 24 divided by 3, and that will be 8.0 ohm. Here, you see, if you are not fortunate to think this way, you may be tempted to use 1 over RT, which is equal to 1 over R1 plus 1 over R2 plus 1 over R3. If you use this, because you don't know R2, you can't be able to find the total resistance. Rachel. Rachel, your hand is up.
Yeah. So, Mr. Ijia, what if you go and do number 4 first and find R2 before you come to find
You can
the
do
total?
that. Yes, you can do that. But if you are fortunate to see this quickly, it will also do you a lot of good.
Mr.
What
Ijia,
re-
so you use the is it the same voltage? Like, I don't understand why you're using that voltage.
You see, these are resistors connected in parallel, and when resistors are connected in parallel, their total, the voltage drop or potential difference across all of them is equal to the source voltage. Okay, so it means that the voltage drop or potential difference in the circuit, which is the source EMF, is 24. The total current in the circuit is 3. So if I'm looking for the total resistance, then it should be V total EMF over the total current. That will give you the total resistance. Are you okay? So Rachel, if you want to use number 4, how would you do it? How would you use number 4?
Mr. Ijia. Okay, so first you write the ratio in terms of fraction, like I3 over I2 is equal to 4 and 5. Then we'll find I3 by using Ohm's law, V is equal to IR. So to be I3 is equal to V on R3.
Are you looking for I3 or I2?
We are looking for I2 first.
I2.
I3.
Okay. So I3 is equal to V on
R2.
R3.
R3.
And so you have 24 over 30.
30.
That will give you
So you
I3.
get 0.8 ampere.
So this is equal to 0.8 ampere.
Yes, please.
And so you can
Then
use
you
that to
find,
find I2.
yes, please.
So please let's follow what she's saying. So it means that
Mr. Ija, we can
I2,
just find a relation for I2. Then we'll put it into it so that whatever we get to be the resistance, like direct.
yes, I understand you. So using this ratio, it means I2 must be equal to I3, okay, I3
Yes,
over
please.
4 times 5. Is that not it?
Yes, please.
So
Yes,
that
please.
because she has I3, 0.8 times 5 over 4, which will be equal to,
1 ampere.
so this is 1 ampere. If 1 ampere, then using the same Ohm's law, then R2 will be equal to 24 over resistance, which is 1. Therefore, R2 is 24 ohm. Then she goes back to use this, to use resistance in parallel method to find the total, which is true. But Rachel, it's a lengthy thing. That's why we are discussing it, so that if your attention hasn't come to something like that, you will have it and then apply going forward. Is that okay?
Okay, Mr. Ija, the reason why the reason why I was not very sure about that one was because you see when we're talking about the features of the parallel, you said the current is not the same. So in my mind, I was thinking that 3 ampere is like it's not for all of them.
So this is it. Look here. This is the current coming from the source. 3 ohm is the current coming from the source. When it gets to this junction, it will break into I1, okay, break into I2, break into I3. But I1 plus I2 plus I3 must be equal to the source current, which is 3. Rachel, are you okay?
Yes, please.
So that's how it is. All right, so we are learning. So next time you could know how to also apply that. Okay, so the next question is that we have to find the current in R1. And this is simple. Current in R1 is simple because we know the voltage across R1, which is 24, and then the resistance R1 is 20 ohm. Therefore, I1 would be equal to, oh, the question is about R1. Oh, current, sorry. So I1 will be equal to V over R1. So 24 over 20, which will be 1 point what?
1.2 ampere.
1.2 ampere. What is the potential difference across R3? Yes, let me pick somebody to answer this. Anybody? What is the potential difference across R3? Yes, let's not waste time. What's the potential difference across R3?
Mr. Ija.
Hurry up. Go ahead.
Please, I think it will be 24.
What's the reason?
because the same voltage is supplied throughout.
Exactly, because all the resistors are connected in parallel. Okay, so if we found the resistance of R2 and we got 1, power supplied to the circuit. How do we determine the power supplied to the circuit? Yes. Somebody to share what you've seen with us. Edubia, can you share whatever you've seen with us? How do we determine the power supplied to the circuit?
Mr. Yeah, I'm very confused as I'm seated here, so I'm waiting for you.
Okay, so okay, Ishra. Hey, Ishra, bye. Say, Ishra, before you go, say bye.
Mr. Atia,
Yes.
yes, I was thinking we could use P is equal to V squared on R, since we know the V and R.
Okay. So V is equal to V squared on R. Now, now we put that we can also use I squared times R. We can also use IV. If we use
Mr.
V,
Atia,
hello.
okay, fine.
If we are to use V squared on R, okay, V24 squared. What is the total resistance or the equivalent resistance?
8.
What did we get as the equivalent resistance?
8.
8. So 8. If we are to use I squared on R, I is 3. So 3 squared. What is the total resistance in the circuit? And 8. You are confused. 8. If we have to use IB, 3 times 24, check. We must get the same value. So check it for 1, 2, 3. Check the answers for all
Mr.
of
Yeah,
them.
you get the same value.
We get the same value throughout. So that is how to go
72.
about the power supplied to the circuit. Please, any question? Any question? No question.
Please.
Let's move on.
Mr.
So,
please wait 1 minute.
okay. Please hurry up. So we've dealt with when you have questions relating to parallel connection. We are going to look at when we have a combined circuit. A combined circuit is made up of series and parallel connections. The two arrangements put together. How do we analyze a combined circuit? Hello, Priscilla.
Have you done fourth question?
Pardon?
The fourth question.
No, it's not a question. We are going to look at we've looked at series parallel, and I'm talking of a combined circuit. Okay.
No, the question we just solved, like the fourth one. If I3 is the ratio, this one.
Yes. What is the resistance? At R2, did we get 24? Yes, that's it. It's here. Or how we solved it is is what you are asking them.
Yes, because I
Okay.
think it.
Okay, so Rachel even contributed to that effect. Okay, if we are to use I3 over I2, because the ratio of I3 to I2, we have 4:5. Okay, now knowing R3 and knowing the voltage, we can find I3. Because V3 is equal to I3 times R3. V3 is equal to the source voltage. So 24 is equal to I3 times 30. Therefore, I3 is equal to 24/30. And Rachel said this 0.8, correct?
Yes, please.
Okay, so 0.8. So Priscilla, we have I3. Okay, if we have I3, then we can use the ratio to find I2. Because I2 therefore is equal to 5 times I3 all divided by 4. So 5/4 times 0.8. Priscilla, what's the answer? This is it 1 ampere?
It's 1.
So this is 1 ampere. So if you have the current flowing through the resistance R2 to be 1, knowing that V2 is equal to I2 times R2, and then V2 is equal to 24. Current,
Okay, there is.
so you get the current is 1. We have R2. Are we okay?
Yes, please.
Okay. So if you have a combined circuit, the combined circuit is made up of, this is an example of a combined circuit. We have 2 or more resistors in parallel. So R1, R2. These 2 are connected in parallel. Then we have 2 other resistors. This is R3. Okay, let me make this as R1, R2, R3, R4. Connected to a source voltage. This is an example of a combined circuit. Why combined? We have parallel arrangement. R2 and R3 are in parallel. This parallel circuit is in series with R1 and R2. Okay, so this is what we call as a combined circuit. A combined circuit. How do you deal with a combined circuit? You have to resolve this to look like a single circuit. So you find the equivalent resistance of these 2, and you know RT is equal to R2. Don't forget, when we went through 2 resistors connected in parallel, we have the total resistance to be 1 over R2 plus 1 over R3. when we went through the LCM method, we saw that then RT would be equal to R2 times R3 over R2 plus R3. So let's assume this is equal to, okay, RT. So this equivalent one is known as RT. So we've had the equivalence of these two resistors in parallel, and this is equal to, so instead of having this, we write a single resistor to represent the two resistors in parallel, and this we are calling as RT. So it means that the equivalence of the two in parallel is now in series with R1 and then R2. So the final resistance in the circuit is equal to RT plus R1 plus R4. This will be the final resistance in the circuit. Please, are we okay?
Yes, please.
Let me use values or numbers to represent what I've done. Assuming we have this is 5 ohm. So these two resistors, this is also 4 ohm. They are in parallel. So these two resistors in parallel are in series with, this is 2 ohm. This is 3 ohm. The question is that find the total resistance in the circuit. So I need to tackle the circuit in parallel first, which is this one. Treat this to get that single resistance, which will be equivalent to this. So when two resistors are in parallel, the total resistance is equal to 1 over 4 plus 1 over 5. And RT will simply be equal to 5 times 4 over 5 plus 4. Please do not forget that this method applies to only two resistors. If there are 3, it will not work. So I have 20 over 9. And what is 20 over 9? This is 2.222, correct?
Yes, please.
So that single resistance, which is equivalent to the 2, is what I've found. And this is R equivalent is equal to 2.222 ohm. Meaning that this single one is equivalent, is in series with this, and then this one. Therefore, the total resistance in the circuit is equal to 2.22 plus 2 plus 3. So I have 5 plus 2.22, which is 7.22 ohm. This becomes the total resistance in the circuit. Please, all is well.
Yes, please.
Are we all okay? Okay, then let's move on to what we were doing today. Lord volts, EMF of a cell. Irene, are you done writing?
Please, can you adjust the camera?
EMF of a cell, log volts, and then the terminal voltage.
Please, I'm done.
So, EMF of a cell, lost volts, and then in the laboratory, whenever you are to find the EMF of a battery, if you have to find the EMF of a battery, you have the battery, then you connect wires, and then connect the voltmeter across the battery. And the voltmeter will record the EMF of the battery. So if the battery has EMF of 1.5 volts, you see 1.5 recorded on the voltmeter. And we term this as, when you are determining the EMF of a battery, this is determining EMF of a cell or a battery when no current flows through it. The it refers to the voltmeter, or potential difference of at no load. This is also termed as determining potential difference of the battery at no load. No load. The no load means that there is no resistor connected. Over here, we said when no current flows through it, no current flows through the resistor. The conditions for current to flow are that there must be a source of EMF. The EMF creates a potential difference across the wire. There must be a conductor and the circuit must be closed. Every condition has been fulfilled, yet what we are saying is that no current, when you make such an arrangement, no current flows through the voltmeter. So the EMF E of the battery is equal to V, which is the potential difference or the voltage drop. You see, this expression, no current flows through the component, is said because an ideal voltmeter has a very high infinite internal resistance. So a voltmeter which is 100% efficient has an infinite resistance. So a voltmeter has an infinite, very, very high internal resistance. That is an ideal voltmeter. 100% efficient voltmeter. That's what we mean. So that is its nature. And so in a circuit, when you connect a voltmeter, and that is the only actor or actress in the movie, then be ready to expect that no current or no charge will bypass it to flow within the circuit. The moment the current gets to this point, it cannot cross. And this is the reason why in a circuit, voltmeter is connected across or parallel. Gerard, you will say it is shunted. Please, are you with me? The reason for which in a circuit you must connect a voltmeter parallel to the load. So if this is a resistor, and you want to determine the voltage, the PD, potential difference across the resistor. Of course, determining potential difference, you need a voltmeter. Do not connect a voltmeter in series. V, no. But rather connect a voltmeter in parallel to the resistor. So this is the resistor R. You want to determine the voltage drop across it. Do not connect the voltmeter in series. In series means break the circuit, either this part, break here or here, and put in the device. So it can be here or here. So if I choose this side, then I'm connecting the device here. For voltmeter, it's a no. If this is the resistor, connect the voltmeter parallel to the resistor, and you can determine the potential difference across it. Correct. What is the reason? The reason why we don't connect voltmeters in series is that, you see, current flow is as a result of charges. When charges flow or move, and the charges are within the volume of the conductor or of the wire. This is a wire. So the charges will be in and then be pushed. Now, when you connect the voltmeter in series, the charges still are moving within the conductor. So when it gets to the voltmeter, because it has a very high internal resistance, it cannot move, it cannot pass, okay, or move across the voltmeter because it will resist it. So the charges will not go. Please, are you with me? Hello, are you with me?
Yes, please.
So,
Yes.
now, if you still want to measure the voltmeter, the voltage or potential difference across it, the way is that don't put it either here, or anywhere here, because it will block the flow, the free flow of the charges to move within the circuit. So what you have to do is that create an alternate path. Create another path. Connect a wire to this point and then connect it to the voltmeter. When you do that, you are creating an alternate path. But one may ask, but while this is a wire, still current will go through. It's true, because I said that once you connect another third wire, you create a junction. Whenever current gets to a junction, it will break up. Part will go here and part will come here. So this thing will happen. But the point is that when this is I1, I2, when I2 gets to the voltmeter, because it has a very high internal resistance, I2 cannot pass. It will come back to this part and go. Okay, so yes, current will still flow through this, but when it gets to this, okay, it cannot continue. This will block it, so it will come back to the original path. So by creating an alternate path, current can still go through this when this is also there. The reason for which, when you want to determine voltage drop or potential difference, we say connect the voltmeter across. Please, are you okay?
Yes,
Yes,
please.
please.
If it is the voltmeter,
Mr.
this
J,
is, hello,
please can you repeat what you said?
okay, listen to it. So when you want to use a voltmeter to determine the potential difference, we say that connect it across in parallel. By connecting it in parallel, you are creating, you've realized that when it is directly within this circuit, anywhere here, current will not go. So give it a second part. The second part is the parallel connection. Now, when you give it a parallel connection, while this is a wire, charges from the source or current from the source, when it gets to the junction, would break up. Part will go here, part will go here. Okay, but this one that is I2, which is coming through this, cannot go because voltmeter is there. Meanwhile, this is going. Okay, so it will, because it cannot go, it will come and join this to flow within the circuit. So it is like no current is going through this. It will come in and take this path. But by connecting it across, you can still determine the potential difference, and then current will still flow. That is what I'm saying. On the other hand, if it is ammeter, look at the behavior of an ammeter. A voltmeter has a very high internal resistance and an infinite internal resistance. Then an ammeter, an ideal ammeter, an ammeter which is 100% efficient. An ideal ammeter has almost zero internal resistance. The opposite of this. So an ideal ammeter put it there for me, has almost zero internal resistance. Very, very small. The reason is that, yes, the function of an ammeter is to measure current flow. So it must be designed in such a way that it offers no opposition to the flow of current. It offers almost no opposition to the flow of current. And by designing it as such, you can measure maximum current. Imagine if it is designed to have a very high internal resistance. It means it would oppose a lot of current and then measure small. And when it is designed in that manner, it has defeated its purpose. Please, are you okay? Are we okay?
Yes.
Hey, are you there?
Yes, please.
All right. So an ideal ammeter has almost zero internal resistance, so that it can measure maximum current in a circuit, ammeter must always be connected in series. In a circuit, an ammeter must always be connected in series. In series. So let's come to this circuit. So if I have a circuit with a resistor, to measure the current flow, I must connect the ammeter in series. Here, break the circuit, either this part or this part, and push it in, whichever way would work. And this is because the current charges always flows through the volume of the conductor. So these are charges. So if you want to measure how many charges are crossing every second, then cut the conductor and push the device, connect the device to the conductor. And this would measure the number of charges crossing to give you current. So it must be connected in series. The moment you break the circuit and push it is in series. Please, do you have any question?
No, please.
All right. So when you have a circuit and you want to determine the EMF, connect the EMF in parallel to the circuit. And you have the EMF at no load, or EMF when there is no current flowing through. Now, and when you do that, you have the source EMF E equal to the voltage drop across the voltmeter, which we call as terminal voltage. So the terminal voltage VT, termed as terminal voltage, is the voltage drop across the voltmeter. Now, when we connect an external resistor, into the circuit, by external resistor, this is what I mean. Let me draw another circuit. This is the EMF E of the battery. The battery has an internal resistor. So there's an internal resistance R within the battery. So when we connect an external resistor R, this time when we connect a voltmeter across the resistor, something happens. So the difference is that earlier we had the voltmeter connected to only the battery, and we got the EMF being equal to the voltage, the terminal voltage, or the voltage across the voltmeter. Then this time, even when there was an internal resistance placed, okay, this applies even when there is an internal resistance. Then this time we connected an external resistor R into the circuit. But when you measure the potential difference across the resistor, which is the terminal voltage, this time you don't get EMF of the battery is not equal to the voltage drop across the voltmeter, which is the terminal voltage V. So we investigate why. And theory makes us understand that when you connect an external resistor, it's as if there is a lost voltage because it is not equal to, so it means the EMF E plus the voltage drop across the resistor plus what we call lost volts. Part of it is lost. When we are able to find what is lost and we add it to the voltage drop across the voltmeter, it must be equal to the EMF E of the battery. Okay, and the moment this lost volt is as a result of the internal resistance of the cell. So the lost voltage or volts is as a result of the internal resistance of the cell or the battery. And it shows up whenever an external resistor is connected. If you haven't connected an external resistor, you still have this equal to this. But the moment you connect an external resistor, you realize that this will not be equal to this. There will be a lost volt. And the loss is as a result of the internal resistance R. Please push an R here. The internal resistance R of the battery. Please, are you okay? Are you okay?
Yes.
Hey, young man, if you have any question, ask. Now, if there is an internal resistance or an external resistance, please, this is what happens. The circuit always appears as if the internal resistance R is also in series with the external resistor. So we have a big R, and it's as if small r is in series with the big R. Now, when you close the circuit, current flows through it. Okay, so the current I passes through R and also passes through small r. So we realize that the EMF of the battery will be equal to the current, the terminal voltage big V plus the lost volt small v. So EMF is equal to big V plus small v, where big V is the terminal voltage and small v is the lost volts. If small r is in series with big R, then it means that the same current I would flow through both resistors. So we have E is equal to big V is equal to I times R. The current I times the resistance here would give us the voltage drop across the resistor. So this is it. Then plus the same current would also flow through this. So the lost volt is also equal to I times small r. So take note that big V is I R, whereas lost volt small v is I R. We'll be using this to solve a lot of questions. So if we simplify this relation, we have E is equal to I out, R in plus small r. And this is the relationship connecting EMF of a cell, the terminal voltage, and then the lost volts. Or sometimes we can also conclude that the lost volts, small v, if you are looking for the lost volt, is equal to the EMF of the cell minus the terminal voltage, which is the voltage across the resistor. So this is the concept of lost volts, EMF, and then terminal voltage. Please, if you have a question, ask. Now, what is EMF? EMF of a cell. We define the EMF of a cell. We define the EMF of a cell as the work done in carrying a unit charge from the lower potential of a cell to the higher potential. So this is the lower potential minus, this is the higher potential positive. So the work done in carrying a unit charge from the lower potential through to the higher potential is what we term as EMF, electromotive force of a cell. So the electromotive force of a cell is defined as the work done in carrying a unit charge from the lower potential of a cell to the higher potential of the same cell. That is the definition of EMF of a cell. And it's because it's similar to or the same as the voltage drop across the battery, its SI unit is also expressed as volts. Volts. Please, is that clear?
Yes.
All right. Please, if you have any question, ask before we call it a night. Tomorrow, there will be another session, and we'll solve the Mach 1 electricity question, the Mach 2 electricity question. Then we look at how to charge post electricity. Okay, we have Kirchhoff's law and then potentiometer. Kirchhoff's law, I want us to do that in school. Then potentiometer and the Wheatstone bridge, which also has some practical application. We'll do that in school. So when we look at how to post electricity, then from there, we'll solve Kirchhoff's law and Wheatstone bridge and that thing, the potentiometer one. Then we'll begin with AC theory. I want us to start AC theory. If we could finish it before we go to school, it will also help us. But once we've done this, we can easily do that. And then, okay. So,
Mr. Bia,
hello.
please can you redefine the EMF?
The EMF of a cell is defined as the work done in carrying a unit charge. A unit charge. 1 coulomb. A unit charge means 1 coulomb. A unit charge from the lower potential of a cell or battery to the higher potential. In a circuit, please, the negative pole is the lower potential. The positive is the higher potential. So if a unit charge is moved from this point through the circuit and ends at the positive terminal, that defines the work done. Okay, and the work done in doing that is what we term as the EMF of the cell or a battery. All right. So if you don't have any question, then we will call it a day. Nanadwa, Andre, and Co, Requia, Irene, Priscilla, and Rachel we'll continue tomorrow. I'll let you on the platform. Okay. So
Yes.
good night to all of you.
Good night.
Okay.
Thanks.
All right.
Bye.
Yeah. Okay. Bye-bye.